Right, so the next speaker, ready, Thomas Grimm and Damian from the Heisteeg. And the title of the talk is Reconstructing a Finite Flux Landscape. Please.
Well, thank you very much. Can you see my slides?
Yes.
Perfect, thanks a lot. Yeah, so, well, first of all, thanks a lot to the organizers for putting together this nice workshop. It's indeed great to have the community together, even in these more complicated times. My talk will be about reconstructing a flux landscape, and it will be based on some paper which appeared last fall. And in fact, at least 3 upcoming works with two of my students, Damian van der Heisteeg and Jeroen Monet, and a postdoc, Brice Bastien, and a number of mathematicians. I will mention these papers at the very end. Okay, and then these 2 will hopefully appear soonish. So let me start with some very general remarks, just to get us into the mood, so to say. Well, everyone who worked in string theory makes quickly this observation that scalar field spaces and scalar potentials are remarkably constrained. And in fact, the Swampland program is aimed to generally formulating and understanding these constraints, and it kind of directed us into new ways of looking at these problems. So for example, we want to understand what are universal properties of the allowed field spaces and scalar potentials which can arise in string theory or in quantum gravity in general. We can ask, can we establish, once we know the scalar potential, can we establish finiteness statements about the vacua? And finally, what is the structure of the string theory landscape? Of course, these 3 questions are very general, and as of now, we are not able to answer them in this generality. But what we can do is we can start with an example which is rather well controlled, and maybe the best controlled example we have so far in string compactifications, namely type 2B or F theory flux compactifications. And in fact, also in the previous talk, we heard a lot about these sort of flux compactifications. But let me recall some very basic statements about them. So first of all, they have a G4 flux, which is quantized. This can also be half quantized. It has a 10-pole constraint, which is that this quantity squared is bounded. And then if we compute the potential, just the classical flux potential, we find this expression. Yeah. So this is, in fact, a rather complicated beast. Even so, it looks simple when written in this condensed form, but it's rather complicated because it depends on this Hodge star, and this Hodge star can vary over the field space, in particular over the complex structure moduli space. And what I want to do is I want to understand kind of this dependence on the complex structure moduli. I will call this field space M. So there are long-standing questions about this scalar potential. First of all, it's almost 20 years ago, the question was posed, are the number of solutions or vacua where this is where the scalar potential vanishes, or we have a Minkowski vacuum, are they finite or are they infinite, or what are the constraints? So even if I assume that there are just finitely many Calabi-Yaus, it's not known if there are finitely many vacua which have these self-dual fluxes. Furthermore, it is not fully understood what is the structure of the allowed spaces M. And so what is the structure of the vacuum landscape is also not clear at this point. However, what I want to convey in this talk is that we are now able to answer these questions. So why is this actually complicated? Well, first of all, it's a genuine n equals 1 setting. So what does that mean? It can be formulated in terms of a Kähler potential and a superpotential, which depends on the 4,0 form and the flux, and here on the 4,0 form. I will not talk about the Kähler moduli dependence. Well, another reason why this is complicated is because the periods, so the functional dependence of these integrals on the complex structure moduli is in general very complicated, and it's very hard to see any properties of this. So if you just, especially when you have multiple moduli, if you just stare at them, you don't see any, you think maybe everything is allowed. And thirdly, finiteness questions are in fact very hard, extremely hard mathematical problems, like even from the abstract point of view. That might come a little bit surprising, because you might think, well, I can take the Tedbull constant G4 wedge G4, write it with a Hodge star, and then this is bounded, so there must be some sort of finiteness involved. However, the important point to note is that this moduli space M is in fact not compact, and that that means that the Hodge star in fact can degenerate. So this Hodge star here, which appears here, can degenerate, and so in principle there could be infinitely many fluxes which satisfy this condition. So the key challenge is to cut off infinite tails of vacua near every boundary. So in the bulk of the moduli space, the question is clear, but in the boundaries of the moduli space, that's where the complication lies. Yeah. So we have to control the periods or the Hodge star near every boundary region in field space. Now, let me discuss how one does that in practice, and do that with some geometric considerations first. So now let's consider a one-dimensional moduli space for illustrative purposes, and let's look at it here for example. So say for the mirror quintic Calabi-Yau threefold, you have a real two-dimensional moduli space, and at special points, this Calabi-Yau manifold degenerates, say the large complex structure point or the conifold point. So that's kind of the picture of the moduli space you should have. And these spikes here, they can be of infinite length, like in the large complex structure case, or of finite length, like in the conifold case. That's where the tricky parts lie. So what can we do in order to attach some informations to these spikes? Well, the first information which we can collect is the so-called monodromy around these points. So if I encircle them, then something can happen to these period integrals, and what happens to these integrals can be encoded by a monodromy matrix. We actually do something slightly refined or slightly different. We take this monodromy matrix T, in fact, the unipotent part, but it's not so too important, and we take the logarithm of this. Right? We take the logarithm of this monodromy matrix, and then we find a matrix N, which is now a nilpotent matrix. And a nilpotent matrix, you can just think of as something, if you take a kth power of high enough power, it vanishes. And you can think of it as something like a lowering operator. Now, unfortunately, that's not yet enough to classify the boundaries, but what we have to attach as well to each boundary is somehow the limiting behavior of a PQ form when you go to these limits, to these boundaries. And there a mathematical results comes to our help, namely that to whatever boundary you go in complex structure moduli space, your spaces F, which are a convenient combination of the PQ forms such that they are depending holomorphically on the coordinates, they actually take this rather, well, seemingly simple form. Yeah, I warn you that it's just seemingly simple form. So it has a kind of a polynomial part in front, and the first part. We are in the limit where the imaginary part of y is very large. So, and an exponentially suppressed part in which can correct this. Okay, and in fact, this polynomial part in T, in these limiting coordinates, it has a name, and it's called the Neopotent Orbit. It's just a name, but it can be defined with certain special properties. And then these strongly suppressed corrections can be neglected. And this is actually possible near every boundary which you have in moduli space. So now the key point is whenever having any coordinate close to a boundary or in any limit, the correct objects to study is the nilpotent orbit. Yeah, it contains all the information, or it contains the crucial information about the boundary which you consider, or the limit you're considering. And one thing which we also at first underappreciated is that the nilpotent orbit does not only contain information about the perturbative terms, right? Then it would mean that it's just in certain limits useful where everything is in the perturbative information. In fact, what one finds, and Damian will say more about this in the second part of the talk, is that in most limits, the nilpotent orbit contains information about the non-perturbative corrections. So in fact, if you understand all the limits, you understand what kind of non-perturbative corrections you have to have in each limit. So what is the picture which we have now developed? Near the boundaries in moduli space, we can associate to each of these boundary region a nilpotent orbit, right? But unfortunately, it turns out that this is not yet the most useful perspective, right? Because these nilpotent orbits are actually really complicated objects, especially when you have many variables. There is a better way of looking at this, and this is by kind of taking a reference structure and introducing a function h. But it's not really just a function, it's actually a real group valued field on the moduli space. Yeah. And it interpolates between a reference structure and this nilpotent orbit. And what we do now is we introduce a field theory on the moduli space, an auxiliary field theory to describe this field H. And this is the holographic perspective which I was suggesting in this last year's paper. So how does this work? So first of all, this field H is a group valued field. So we write down a sigma model action for it. And this is the sigma model action, which was also suggested by Chicotti. So this fits nicely with his proposal. And this is the sigma model action. It is not really a Westerminer-Witten model in the sense that there is also the reference structure plays into the game. So if you look at this action, the dagger here is with respect to this inner product in the reference structure. As an aside, one can try to couple this theory to gravity on the moduli space. And there exist actually two different proposals by Chicotti and mine. And they actually differ in the sense that when one looks at the two-dimensional setting, the proposal which I have put forward is more like a proper two-dimensional gravity theory, like JT gravity. And then you find that the physical moduli space metric, like the Weil-Patterson metric, comes as a solution to this theory. So it's quite fascinating. No idea why this is true, but it seems to be true. Okay, but back to the main line of the discussion. So now, what is the question? Now we have this field theory, and we want to understand what are the asymptotic solutions in this field theory. And in order to fix them, we have to impose some conditions on the solution set. First of all, they have to have a symmetry, which is motivated by the fact that there's kind of, we are thinking about nilpotent orbits. They have this shift, this monodromy symmetry, which is now continuous. And they satisfy a certain condition, which is with respect to an operator Q, which takes eigenvalues P on this reference structure. And the remarkable thing now is if you impose these two conditions, then your asymptotic solutions actually look like, also know, as you know from ADS-CFT, that you have kind of an overall scaling part. And then you have an infinite number of terms, 1 plus G1 plus G2, with corrections which are suppressed with some kind of radial coordinate. And this radial coordinate is exactly the coordinate which we send to the limit. Okay. So now, now what does that do for us, or how can we now use this? Well, these meta solutions exactly lead to these nilpotent orbits, namely the thing which classify each limit, if we match this with some Sl2 boundary data. So what is this Sl2 boundary data? It states that at the boundary there is a Hilbert space, which splits into a PQ decomposition, and this can be parameterized by some operator Q. Then there is an Sl2R algebra associated to this boundary. And this Sl2R algebra arises from completing this N, so this log monodromy matrix N, into a complete triple, right? And finally, there is a phase operator, delta, which kind of tells you how the real structure is embedded into the complex, into a complex space. So if you specify these three data, and they are very simple in examples, you can recast the near boundary solution. So this is a well-defined set of boundary data which can be associated to every boundary. And I listed here them only for codimension 1 boundaries. In fact, the data 1 and 2 can be classified. And for Calabi-Yau 3 folds, for example, that leads to 4 H21 different 1-parameter limits. And the interesting part is that this phase operator seems to contain much of the non-trivial information. And it would be very interesting to understand what is the physical theory for this phase operator. So if there is some really like a full holographic picture, you would expect that at the boundary, there is a theory for this phase operator. And so maybe in one of these proposals, there is actually a clear understanding what is this phase operator. In examples, you find that it depends on theta values, for example. So it's a non-trivial object. And as I mentioned, the amazing thing is that you can use now this to reconstruct the bulk. Yeah, so you can write down field equations for this effective auxiliary field theory on the moduli space, and then you can translate them into recursion relations. They are very non-trivial recursion relations, and then stepwise reconstruct the bulk solution. And what you have to impose is a single matching condition between the bulk and the bulk and the boundary data. So the simple matching condition fixes the solution. So now we can reconstruct the near boundary solution near every boundary using the simple data. And this is, of course, also true for the Kähler side by mirror symmetry. So you have a very efficient way of classifying Kähler moduli, Kähler cones. So why is this perspective useful? Well, I actually told you 3 perspectives already. There are the periods, there's the nilpotent orbit, and then there is this field H, which has these Sl2 properties. Yeah, and the fact is that the last one follows Sl2 representation theory, and we can prove properties of these coefficients in Sl2 representations. So I can control this infinite series of corrections to my field H. So the Sl2 splitting is the main tool for classification. you can now try to build models with that if you want to have a certain feature in your boundary theory or in your moduli space. And you can use it to uncover the structure of the flux landscape. In fact, that's exactly the tool which is used to prove the finiteness of the flux landscape. So let's go back to the question. The question is, how many self-dual fluxes are there? Are there in fact infinitely many or only finitely many? Well, what one can now do is one takes the Hodge star and writes it in terms of this field H. Remember, H had this nice expansion into suppressed corrections, which we can control with Sl2. So these we control via this holographic approach. And then we have the Hodge star on the boundary, which is part of our boundary data. And now we can discuss how in a codimension one limit, how this works. And the general story I will mention only briefly. So what is now the idea of this finiteness proof? Well, the idea is you take your fluxes, you decompose them in Sl2 representations, so into Sl2 eigenspaces. And then if you just take the leading part, then you find that they either grow or they decay near the boundary. But by tadpole cancellation, this has to be bounded. So I should better switch on only fluxes which are decaying near the boundary. But because of the self-duality, the upper fluxes and the lower fluxes are related. And therefore, you can, if you switch on these fluxes, you also have to switch on these fluxes. And so you cannot switch them on at all after a certain point in the moduli space. So this gives a simple, intuitive way how to see the finiteness. However, life is not that simple. Otherwise, one would probably have found this already before. The tricky part is now to show that this is also true if you include these corrections to the Hodge star. And there you need exactly these properties with respect to the Sl2. So it's a quite beautiful mathematical statement. And to indicate a little bit how non-trivial that is that for the SUSY configurations, the analog thing has been shown in a very famous paper by Catani, Delin, and Kaplan, which is often viewed as the strongest evidence for the Hodge conjecture. Now you might ask, so how can we generalize this? Our question is even more general than their question. Well, we use some recent breakthrough in mathematics, which relates Hodge theory with tame topology and O-minimality. So with model theory. And the remarkable thing is that finiteness is built into this structure. So we can prove the finiteness, and in particular, we also discover what is the minimal structure of the flux landscape, of the vacuum landscape. Now one can ask what is, if this can be extended beyond the flux setting. But this is work in progress, and I hope to report in the future on this. So this brings me to the end of my part, and let me hand over to Damian's.
Okay, let me share my screen. Can you all see me switching slides? Great. Okay, so I'll now take over from Thomas, and I'll try to make the story he told you so far a little bit more explicit. And the idea is to do this by looking at the periods. So let me first say some general words here. And the idea is that when we're looking into, So when we're looking into Calabi-Yau compactifications of your favoric string theory, then basically all the physical properties of this 4D theory that we'd like to study are determined by these periods. So when we want to answer a question like how many flux vacua there are, or whether a certain Swampland conjecture holds true, it basically boils down to how well do we understand what these periods look like. Now, when we go to a point in the moduli space like the large complex structure point, we know them very well. we know that we can express them in terms of the intersection numbers of the mirror Calabi-Yau manifold. And this gives a very good description of the moduli space around there. But when we move away from this lamppost and go to something like the conifold point, general techniques are rather lacking. And it's a very hard problem to have some general description of the periods for points away from this lamppost. And the reason for this is that non-perturbative terms in this expansion for the period vector start to become much more important when we go over here. And now the point that I want to convey, or one of the points I want to convey in the remainder of this talk, is that we can use this mathematical structure even to make these non-perturbative terms more precise and give a better description of the structure of the periods. So let me first try to connect back to what Thomas talked to you about and think about this group valued matter field H and discuss what it looks like for an example. So recall that the boundary data is specified by some charge operator which encodes a decomposition into PQ forms at the boundary. It has some Sl2 algebra that satisfies the standard commutation relations, and this is complemented by some phase operator that can be decomposed in a particular way with respect to this Sl2 structure and this charge structure. Now, a convenient point of view here is that this boundary data can be classified. And by this, I mean that we can classify the spectra that are allowed for the charge operator and for this Sl2 algebra. Now, when you consider, for instance, a Calabi-Yau threefold setting with one modulus, there are only 3 possible boundaries. You can then write down the most general set of boundary data for each of these cases and run this bulk reconstruction algorithm. So let's take a look at an example, and let's look at this conifold point. So the boundary data looks like something like this. We have this Sl2 triple, which is basically the simplest, the most minimal triple that satisfies these commutation relations. We have a charge operator over here that satisfies these compatibility commutation relations. And based on this data, you can check that this indeed reproduces a type 1,1 singularity, which is the singularity type that we associate to a conifold point. Now, we need to extend this data with this phase operator, and when we check for the possible maps that have the right weights and charges, then we find that only this lowering operator, the log monodromy matrix, has the correct properties. If you go to something like large complex structure, we can also solve the problem, but it's a little bit more complicated, and here you would need to introduce this alpha prime correction that appears with the Euler characteristic. But for the conifold point, let me stress that this is indeed the most general thing we can consider for our boundary data. So when we now run this recursion algorithm, we find actually that it's already, even though this boundary data looked surprisingly simple, you already need to solve an infinite series for the recursion. And we find that these coefficients gk take this form. And if we then plug it into the expression for our bulk field matter field, we find that the solution takes this form. Now, when we want to say we want to connect this to a more familiar formulation of things in terms of the periods, then you could try to say compute the Hodge star on this moduli space. And when you want to do this with the period vector, it turns out that to reproduce the result from this bulk matter solution, you actually need to go up to secondary and instanton expansion. Because when we are at the conifold point, to leading order, the period vector just is encoded by this 1 and this I. And all the interesting stuff, such as the monodromy behavior, which we get from this logarithm term, for instance, appears through the instanton expansion. Now, if you are just given this, if you are given this match here for this particular example, you see like, okay, we need to include instanton corrections, there's no other way. But we can even argue more generally why we need to include these instanton terms in the period vector. So how does this argument work precisely? Well, for Calabi-Yau threefolds, we know that we can generate any 3 form by taking the 3-0 form and taking derivatives with respect to the moduli space. Now, if we plug in the form of the period vector close to the boundary, we see that the derivative either hits this monodromy behavior vector or it hits this non-perturbative vector. And we end up with something like this. Now, at the conifold point, the monodromy acts trivially on the leading term. So this means that when we look at how the log monodromy matrix acts on the perturbative term, it just annihilates it, which means that in order to span the full vector space, we need this term A1 to be present. And the reason why I want to stress this point is that this mathematical formalism doesn't just tell us how the 3-0 form degenerates at the boundary, but it tells us how the whole vector space degenerates. So we need to be able to say something about other PQ forms like the 2-1 form as well. More generally, we can actually compute an upper bound on the vector space that is spanned by A0 and its descendants through log monodromy matrices. And we find that unless we're at the type that classifies the large complex structure point, we cannot span the full vector space. In other words, if we move away from this large complex structure lamppost, we need to include non-perturbative terms in the expansion for our period vector. And this complements the result of these two papers from last year very nicely, where they found that in an n equals 2 supersymmetric or n equals 1 supersymmetric setting, unless there is some sense of more supersymmetry left, you need to include non-perturbative terms at the large complex structure point. And this observation here now extends it to other points in the moduli space. So you might now think we take this expansion for the period vector and we can just turn on the terms that appear in this expansion. We say like, oh, for the conifold point, we need to include A1 and A2. We just turn them on. But this turns out not to be the most convenient approach. And in fact, it is more convenient to recombine this expansion in something I'll refer to as the instanton map. And we basically factorize the expansion in non-perturbative terms into this exponential of this matrix valued field. And the idea is here that this map satisfies some useful properties such that it is holomorphic in this variable, it vanishes at the boundary, and it can be decomposed in a particular way with respect to this charge operator Q infinity. And the point why this formulation in terms of the instanton map is more convenient is that we cannot just take any period vector, but our period vector needs to satisfy some consistency conditions, transversality conditions, which take this form. And now when you plug our expression for the period vector into this constraint, you find that you actually need to impose some differential conditions on the instanton map. And these turn out to be actually really easy to solve when you just take some holomorphic expansion for your period vector. And the idea is now that we can use this formalism, we can use this instanton map to basically start from the possible boundaries in 1- and 2-dimensional moduli spaces, write down the most general instanton map that works there, and then construct via this algorithm our period vector. So let me make this a little bit more explicit and go back to the conifold point. Then the most general instanton map that we can write down takes this form. We can plug it into the transversality conditions, solve them with some leading order expression, and we end up with this expression for the period vector. Now, let me note that this maybe looks a little bit off for you from the most familiar expression for the period vector, because it's evaluated not in the standard prepotential basis, but I'd like to guarantee you that it's the same thing, where this A1 here and this C are just model-dependent numbers, and depending on the moduli space of which Calabi-Yau you're in, say the quintic or some other type, these parameters take different values. And another thing I'd like to stress here is that, well, while I've been demonstrating this for the conifold point, we did not need to start with this 1-1 boundary, and we could have taken any other boundary in the moduli space if we wanted. And it would have worked as well. So to conclude, let me first talk about my part of the talk. And we've seen actually that all this mathematical formalism is surprisingly suitable to build models, local models for our Calabi-Yau moduli spaces. Either we compute this group-valued matter field H by solving these CQS recursions and so on by Catani, Kaplan, and Smith, or we, in a more familiar language, we try to write down the period vectors for whatever boundary we're considering. Alternatively, as Thomas talked to you about, we do not even need to be this explicit, and we can just use general properties of our solutions in order to describe what the moduli space looks like. And depending on the angle you'd like to use, either you'd prefer working with quite general examples, or you prefer working with some general techniques, you can now try to think about swampland conjectures, try to say something meaningful about whether they hold true, and prove something like their finiteness. In either case, I'd like to say that the upshot of these procedures, of these techniques, are that you don't have to be restricted to a particular example, and that these techniques apply for any moduli space that you'd like to be considering. Thank you.
Thank you. Thank you, Damian and Thomas. So we have some time for questions and comment. And Kumran raised hands. So Kumran first.
I'm just clapping. No.
Oh, this is clapping. Ah, okay. So not raising hands. It's kind of confusing. There is a clapping, and then there is a raising hand. Nobody's raising hand. Oh yeah. So Miguel is raising hand. Okay. So Miguel.
Yeah. Thanks for the very nice talk. I have a question for Damian. So you're talking about so you're basically able to figure out the period vector and the general expression generally, but you have these coefficients, right, that you mentioned depend on the Calabi-Yau you're in. Like there's this A1 and C, and Quintic detects some values, and some other Calabi-Yau take different values. Do you know if there's any way, even in principle, to constrain or to make predictions for, or to exclude perhaps some values of these coefficients? Kind of like, what you do in the bootstrap, you say that, oh, some values of coefficients are not allowed. Is there any idea, or is that possible in any way? I don't know.
That's a very good question. We can get some kind of positivity conditions sometimes related to these values, and that when we, for instance, evaluate something like the Kähler potential, then the coefficient that appears with this non-perturbative term should be positive. We can make these kind of statements, but at least our constraints kind of seem to die down once you go beyond these essential terms in the expansion.
Okay. Are you satisfied, Miguel?
Oh yeah, sorry. I just gave the thumbs up, but maybe.
Okay. Monkey, you are the next.
Hello, Damian. Thanks a lot for the great talk. Related to the question that Miguel asked, is it possible to use partial t omega wedge omega and partial t square omega wedge omega equations to solve the higher order instanton corrections iteratively around any special points in the moduli space, including like the conifolds? What I want to do is, for example, give you the very first terms, like the classical terms, and then use some of the constraints to solve the higher order instanton corrections algorithmically. Is it possible, or?
Repeat the equations you wanted to use?
Like the Yukawa coupling related equations, like omega wedge partial t omega is equal to 0, and omega wedge partial t square omega is equal to 0, or those kinds of things. Because
so I'm not sure
those
if
were.
So I'm not sure if this is an answer to your question, but to get more explicit values for these coefficients, you'd need to think of something like a Picard-Fuchs equation that people typically use to solve for the period vector. And I think it would be very interesting to see what happens when you plug this new ansatz for the period vector, basically, and try to plug it into like the standard Picard-Fuchs equation, and maybe it decomposes in some nice way. Not sure if this is directly an answer to your question, but.
So are you saying that with the Neopotent Orbit theorem, or with the monodromy matrices alone, and with the classical data, it might not be possible to determine all the high order instant corrections, or it might be possible, but we don't just know how to do it yet?
At the moment, I would not know how to yet. At least we can make some arguments for probably the first few terms that we do have control over, such as at the conifold point. But if you go beyond, you need some more input. I don't know if Thomas maybe has something more he'd like to say here.
Well, yeah, this connection has been made, of course, to some extent. Yeah, but the point is, of course, you can always try to go back to the old story of solving Picard-Fuchs equations. That's true. But the idea here is to be more general, not having to enter explicit examples. And then just using general properties. So exactly what Miguel asked and you asked before. And then and there you can extract positivity conditions, but sometimes also quantization conditions of these coefficients.
I see. Thanks a lot.
Okay, Arthur.
Yeah. So, hi Thomas, hi Damian. I have a very simple question about the interpretation of your results. So if I take some flux choice satisfying the tadpole condition, and I add a flux number on some cycle such that the tadpole doesn't change, which in general is possible because, as you said, I mean, the form is not positive definite. So I presume I find a new solution, and I could keep changing that flux number and finding new and new solutions. And I understand your findings such that if I keep going that path, at some point I will find solutions which are diffeomorphic to something I already had. At least it would be one possibility. The other possibility would be that for some reason I don't see you find something that's inconsistent. Can you explain in that language your findings? Is my understanding correct?
Yeah, I think that's correct. Yeah, so essentially you can think of it that you come back in a circle to the old solutions.
In a circle of many discrete solutions. At some
many
point,
discrete solutions, yeah. But
yeah.
So they are just never infinitely many different solutions.
But is it possible to see in that more, I would call it more hands-on way, why if you keep adding fluxes which don't change the tadpole, you at some point must find something diffeomorphic to what you already had?
Maybe, yeah. Maybe
obvious.
there's another way to also see it for such a specific question. But in generality, I would say it's impossible to see it. Because the especially in higher dimensional moduli spaces, it's extremely complicated to control every direction. So just scaling limits or something like this doesn't help. You could have a path which is kind of very winded up or something like this, and you have to exclude all of them. And you have to make sure that you never pick up infinitely many vacua in any path of this sort. Yeah. And that's, so the idea here is to kind of find some sort of orthogonal structure within each sector, which are these Sl2s, and then decouple these various sectors from each other, and then control the finiteness in each sector, and then somehow glue it together into a complete picture. And that
Okay,
this is it's very tricky, and you need, in fact, all these heavy theorems, which we formulated into this physics into this physics sigma models.
Thank you.
Okay. Yeah. Joe has a question. Are you raising a hand?
Yeah. Although I saw Fernando had their hand up first. If Fernando wants to go.
I think we are breaking up.
Well, he was saying Fernando had his hands up for a while.
Oh, excuse me. Yeah. So yeah, I guess
Fernando had their hand up.
Yeah. I think that somehow the color of your hand
seeing it
make it difficult for me to. Okay, Fernando, go ahead. I'm sorry.
Thank you. Thanks for the talk, Thomas and Damian. I just had a very nice question. So, so how is the interplay with other scales in the problem when you move in these flux vacua, like the Kaluza-Klein scale and so on? I mean, when you go to these points like the conifold point or similar ones, is there something to check about Kaluza-Klein mode being decoupled from the flux scale or things like that?
Well, I mean, you mean there could be like a conifold, like a region in moduli space where these scales become close. Yeah,
I mean, typically we just say the Kaluza-Klein scale is here, the flux is here, so we keep the we just stabilize moduli at this scale and we forget about these guys. But I'm wondering that is some singular limits this.
I would say yes, you have to do that if you want to study the full effective theory. You have to do it. Definitely. I mean, the part which we looked at, I hope I made this clear at the very beginning, that we are looking at this flux superpotential part, this flux part, which is even independent of the Kähler moduli, because we decouple these two parts. And I'm saying that even for this part, this question has never been answered in generality. In fact, there are claims that there are infinitely many, like vacua in some tails and so on. And this we can now exclude. Now, the next step, of course, as you point out, is to go to include, say, Kähler moduli, and that's, of course, and see if the structure persists. And then you have to address question like you're asking. Exactly. I agree.
Okay. So I think we're running out of time, but maybe we should add a couple more questions because there are so many questions. Joe, do you want to go?
Sure. I was wondering if I could ask Damian something. And maybe this is a naive question, but yeah, I was just curious. Like you were talking about the necessity of having the non-perturbative objects included in order to not have the vector space degenerate at the conifold. And I was curious what happens when what happens when those non-perturbative objects might if they can if they dynamically can annihilate. I'm thinking about processes like brain anti-brain annihilation, or the condensation of anti-D3 brains into fuzzy NS brains decaying into D3 brains. Like, what does that how would that affect things changing through time, and even what types you have are changing?
Sorry, you lagged a little bit in the middle. Could you just formulate your sentence once more, briefly?
Oh, sorry. Yeah. What happens when the non-perturbative objects that are there to prevent the degeneration of the vector space at the conifold point? What happens when those non-perturbative objects might annihilate with one another, or condense into other non-perturbative objects?
So I think we're using this non-perturbative term here a little bit loosely. When we're at a large complex structure point, there is really a non-perturbative interpretation via mirror symmetry, where we can interpret them as some world sheet wrapping on the dual side. But here, at least from my perspective, it's just an expansion for the period vector in this holomorphic coordinate, and I don't have much of a physical interpretation for this yet. Would be really interesting if we could say something more about this, but at the moment, I don't have an answer.
Okay, thanks.
Okay.